All right. So thanks everybody for joining today. Uh, we have a talk that I've been looking forward to hearing about because this is something that I think is near and dear to a lot of our hearts, especially those of us that work with scientific communities that are trying to move information on an end-to-end basis. One of the things that frustrates a lot of us is having to use a tool like EScp. And our speaker today is Charles from ESnet, and he is going to be talking about hopefully a solution that may be viable in this space. It's a tool that we've been playing around with called EScp, and I always get the name wrong, but hopefully I will get it right in the future. And I'm going to turn it over to Charles to give a little bit of a presentation. And then he said that he doesn't have any demos planned, but I'm sure we can probably goad him into doing one if we ask hard enough. So Charles, if you're ready, you can take it away.
Thank you so much for the introduction, and thank you everybody for joining. I'm just moving my face over here so that I am looking in the right direction. Otherwise, even though I may just be looking at me in Zoom, like I always like to see somebody talking or looking at me. So this is a tool that I started about a year ago. Initially, it was an application to help with tuning our DTNs, and it continues to be an application that will help with tuning our DTNs. And it sort of morphed from that to being a tool for data transfer. So that's the EScp Energy Sciences copy. It is a script, which is Python based, called EScp, and then this data transfer tool, which does the data transfer on our behalf. And I just wanted to talk a little bit about the design of the DTN tool, what makes it fast, what its goals are, and sort of how it works. So at a high level, this is a TCP solution to transferring data at speed similar to iPerf. The idea is if you tune an application, you might start with iPerf. Once you get your iPerf working well, such that you're able to get performance in, in this day and age, 200 gigabit seems to be our standard. So once you get somewhere close to that 200 gigabit mark, or that seems to be our new high level mark, once you get something near to that, you would apply the same configuration you have in iPerf to the DTN tool, and then start doing your transfer. If everything works right, you should get transfers that are right on target with iPerf. If not, there's a ton of tuning options in the DTN utility that will help look at, like, is this a disk issue? Is it something else? And once you figure out where your bottleneck is, it should provide you that close to iPerf tool. Close to iPerf performance. So some of the things that this does, because it is meant as much for testing performance of a machine as it is to actually doing physical transfers, it has a number of features that are meant primarily, are of primary use of people who are like, what is the performance of the system? How can I make it go faster? So one of those things that lets you do is it has a set of IO engines, and you can pick the IO engine that you want to use. Right now, POSIX is probably the standard that everybody will use, especially if you're using a RAID-like array, but it does also support URing. URing is an up-and-coming format for zero-copy parallel IO to SSDs. So if you are doing a transfer and it is on a single SSD, choosing URing as your engine will typically improve performance up to the performance limits of your SSD, whereas POSIX will typically be 80 to 90% of your SSD performance for large files. In addition to the standard, I'm reading from a file, there's also a shared memory engine. The idea of the shared memory engine is, instead of having to transfer a file, this exposes the shared memory layer that DTN implements. And so since this is basically a block-based transfer solution, you can access that block interface and write your own IO engine. It is, I am hoping at some point in the near future to show an example of the shared memory engine being used with something like S3-like storage, so that you would be able to have a file that you start as a regular file on your system, transfer it to a remote node, and then have that remote node store it as a S3 file using the S3 APIs. And when I say S3 APIs, I don't mean like Amazon, I mean any of the competitors to that for object storage. And before I get too far into the details of what happens on disk, I wanted to talk a little bit about what the network side of EScp looks like. One of the first things that you run across when you try to do a transfer is, if you do a regular SCP file transfer, it is probably not very fast, at least when we're talking about like the 100 gigabit speeds or faster. The primary reason for that is that you're going through a lot of layers to encrypt your data, and your stream gets transformed, and every layer you go through, if anything happens like a memory copy, your performance drops significantly, or there's just layers of overhead. I'm not sure exactly what's going on with SSH that makes it so bad, but if you have anything streamed through SSH, you can expect that your performance is going to be limited just based on how the interface works. So one of the concessions we did to performance is, this is a transfer solution that is initiated through SSH, so all your authentication, when you use EScp, all your authentication goes through SSH. You can also use the DTN tool directly and avoid the SSH layer and do transfers without that. But in the normal use case, you do an SSH to another machine. On that other machine, it would load the DTN receiver. On the client, it would load the DTN client, and it would configure it to go over some port. Right now, the default for that is port 222, and that transfer, the bulk of the transfer will be through the DTN utility using keys that are exchanged through SSH. So it will continue to use encryption, just not through SSH, and the data encryption happens through AES, the Galois counter mode, 128-bit. I'm going to go ahead and skip these next two items as they pertain to the what happens when we do the file transfer itself, and I'll come back to that. When we do our transfers, just to give you some idea of the network performance, this is, I think, an unreleased graphic that Ezra came up with, and it could very well be wrong, but it is, I mean, not wrong, but there may be some small errors compared to whatever the release version is. And thank you, by the way, Ezra, if you're here, for providing this graphic. It's beautiful. So this is a comparison of various file transfer tools. So EScp is in blue, Grid FTP, MD, TM FTP, and Zetar is the ZX. I don't know what MD, TM, FTP actually, if there's more of an acronym to that. So as you can see with this blue graph, EScp provides consistently good performance over a variety of file loads. I think this left side probably would be improved by not having the Python front end. When you have a lot of small files, there's a little bit of Python overhead, because the way it presently works is for every file that you specify on the EScp command line, it passes that file through a text interface to the DTN tool, and then the DTN tool is like, oh, okay, I have this file to transfer, and there's a little bit of overhead. As you go to larger files, that performance picks up. I don't know why you would see a small drop here to like 67 gigabits versus 70 gigabits. But this is a tool that is heavily in development right now, so I think there is some performance that probably can be improved there. And this is the currently released version of EScp with all of the features that it has, like checksumming and encryption and et cetera, et cetera. And in some cases, some of that functionality is not fully optimized, I guess. So anyway, going back to the internals of how our network transfer happens, as I mentioned, one of the problems with doing everything through SSH is all of the overhead for a network. So I sort of wanted to pick the simplest way that we could represent data in a way that we can still do encryption on it quickly. So this is the overhead that happens when we add encryption. So every block of data, so typically we're going to be transferring a block of data with each block being something that would fit within the L3 cache line. It's very important when you use EScp that you pick a block size that fits within the L3 cache line. It's also very important that you pick a block size that works with your storage system. So it has to be big enough to be fast on your storage system, but small enough to still not exceed the L3 cache line. In general, since there's no copying that occurs, internally there's no memory copying within EScp. So whatever your block size is will be the resultant thing that goes on to, that gets sent to TCP send and gets sent out over the internet. So in general, so long as this doesn't exceed L3, you will not have any additional memory overhead by using EScp beyond what you would have from a regular TCP session. And really the comparison here would be if you use something like send file, which is a zero copy transfer solution supported by the kernel. How good would EScp relate to send file? And that is a little bit nuanced, but in general, send file will be better, although it's not multi-threaded, so you can have at most one stream per file, whereas this supports multiple streams per file interleaved in the way that I will get to in just a second. So each of these streams that gets generated through EScp, or really the DTN application, is a self-describing encrypted in one-way stream. So that this payload that you see for encryption is one part of it. The second part is where you see the header type. The header type here describes the type of data that is going to be sent. So in addition to the standard, I sent a block of data, there's also a different type of header for describing what the file looks like when it gets opened, or stream characteristics. Like in some cases, you may want to say, okay, I'm done sending files, so there's a different file type for that. And each of those file types contains enough information for it to do its job. But in the majority of cases, you're just going to be sending out a block of data. Each block of data has with it on the network stream, once you get past the encryption payload, a second 16 byte prelude to the block of data. And that's going to tell you what file, when the receiver reads it, what file you're going to be writing to, what the block size is, how much data it should expect, and then the offset to write to on that file. So using those three fields, we're able to take however many flows, have them arrive at the receiver. Each stream is able to be written without looking at other streams, with the exception that in some cases, a stream will have to wait for a file to be opened before it can write that, since the file open information is different from the streaming data. Each of these network frames that I just talked about directly maps to a disk block. The disk blocks in turn are memory aligned in this shared memory region that gets allocated, such that each disk block is aligned across a 4K page size, such that direct IO is supported, which is what makes this sort of a zero copy transfer solution. If you miss, like if you were to do a TCP stream without aligning it to the 4K page size, you then can't write directly to disk in direct mode without doing some sort of intermediate memory conversion. So the whole idea of this zero copy as fast as possible, and that's sort of what everything looks like. So the shared memory structure that I just talked about, in general, it is a large chunk of data that contains everything about the transfer. So it will be some information about the underlying state of what we're doing at the very start of this shared memory region, followed by what IO engine we're using, followed by data that the IO engine itself needs to perform the transfer. So if you define an IO engine like POSIX, you might give it a queue depth of 4, which means there would be 4 blocks per thread. And that's gonna, and then a block size. So if we took a queue depth of 4, a block size of 1 megabyte, and there were 4 threads, we would be looking at overall shared memory size of 16 megabytes, plus a little bit of overhead for everything else that I mentioned previously. So generally speaking, the shared memory is going to be a ring buffer. There's a specific sequence of events. So you start by initialize. When something like the POSIX engine reads a file, it starts by requesting one of those buffers from the shared memory region. At some point, the say POSIX engine would read the file into it, signal that it has done that file read, at which point the network side would look at that same memory region and be like, okay, I'm going to start sending this out through TCP. It would do whatever it needs to do on that block. So in the case of checksumming, it will checksum the data, it then encrypts it, and it then goes out over the wire. Again, there's no memory copies within that. So with this L3 cache, it's a zero copy transfer solution. The only reason that there's a little bit of an asterisk to that is that as you move data, as it gets to the TCP side of sending out data, there typically is going to be a memory copy, especially on the receive side where you have your TCP stream come in, it's sort of unordered data, it then gets ordered by the operating system and copied over to our shared memory region. In some cases, also when you read from disk, you're not going to do a zero copy transfer. And that happens when you, instead of doing direct mode, you go through the standard page table cache. As I mentioned before, this is a block-based transfer solution. It is lockless for large files. So it tries to optimize sort of, in general, you're going to be in general, the thought is that you would be transferring from a large file, in which case you care about locking in the individual blocks, which are relatively small. So it's able to do a lockless file transfer by just sort of using atomics, so GCC atomics, mostly adding an integer to some region. Like if you have a file, you have an offset that you want to read from. When you read from it to start the transfer, based on that offset, which you would increment through an atomic, you then determine where in the file you need to do the read, which then goes on and does everything else. For the actual files, because of the complexity and like you have small files and big files and things can get complicated, there is standard locking for that. At some point in the future, if it was ever determined that sending small files and standard locking was an issue, you could even go with a lockless approach for that, using similar ideas. Sometimes avoiding locking is actually more of a performant hit than just locking using standard tools.
Hey, Charles, we have a question that came in if you'd like to answer it now.
Yeah, absolutely.
So Hans was wondering, can you just briefly describe the difference between a zero copy transfer versus a normal copy? And I guess that is a good question for people who may not be as versed in the literature.
Yes. So as you go at higher speeds, even though your memory bandwidth on paper is super high, like 200 gigabytes per second or higher on a modern PC, as you do this transfer, if you do a copy, you introduce latency, and that latency is typically what kills performance at the speeds that we're transferring. And typically, when you look at a transfer, there are a number of copies. So if you do like a FTP or an EScp transfer, it's going to start off with a copy from the disk going into the operating system caching subsystem, and then from the caching system to EScp. EScp itself is probably going to do several copies because you have to encrypt that data, and the way that you would encrypt it is typically you would take like your whatever you read from disk, and then you would do something to it, which would put it in a new memory region. Once you're in that new memory region, you would go ahead and do your transfer. Every time you switch memory blocks, you have that overhead, and that overhead ends up being really bad really quickly. There's also a problem of how you do the copy. In most cases, when you do a memory copy, you aren't just writing to a location, you're actually reading from your source location, reading from your destination location to make sure that when you do the copy, you're not overwriting data in a way that you're not supposed to. And then you write to your destination location. So even though you have this huge bandwidth of like, let's assume 200 gigabytes per second, with one copy, I just used 1/3 of that available bandwidth. The other problem is as you add pressure on that memory bus, you increase latency for each of the operations that you're trying to do. So now when a packet comes in, instead of the packet being written in, I don't know, like 12 nanoseconds, it starts taking 30 to 35 nanoseconds, at which point you start running into things like dropped packets. And one of the things that's very typical when you're trying to write a tool that tries to be performant is you have sort of like a snowball effect. So like in a normal transfer, everything is good until one of those parameters that affects memory is tuned incorrectly, at which point the transfer sort of collapses and your memory performance goes very badly. Some of this is visible when you look at network tuning. For instance, the TCP receive buffer can strongly affect how all of this plays out. The network card itself has IO rings that are used. So rather than the TCP buffer, there's also like the network card IO receive buffer. That too has to be tuned such that it typically fits within L3 cache. Otherwise, in some cases, your network card itself can be initiating memory copies, which again puts pressure on the entire memory subsystem, which causes this snowball effect. So that's generally why I keep talking about memory copies and why they're so important. So,
all right, thank you.
Okay, good. And did that answer your question before I move on?
Yes, Hans says that helps him.
Okay, awesome. Yeah, so I just wanted to just give a brief, like, if I do an EScp transfer, what's it look like? It turns out it looks very similar to a standard EScp transfer. In this case, I gave it an option to, instead of show the transfer in bytes per second, I had it specified in bits per second. And this is using our new testbed, which is still optimized incorrectly. Thus, when we do this transfer, we're only at 120 gigabits per second. This is over a 200 gigabit link, so it should be quite a bit better than that. But even worse than that, because the memory isn't tuned correctly for AMD processors yet, it goes fast, and then that introduces packet loss, at which point the TCP streams collapse, and then it goes slow, and then the TCP streams pick up and it goes fast. So we're certainly not immune to sort of the same problems everybody else has. The idea is that once this is tuned correctly, that we would have a generic solution that we would be able to provide to everybody. So I don't know how many people use our fasterdata.es.net as a resource to help with optimization. That's typically the first thing that we internally do for our new computers. And then when it doesn't work for some reason, as in the case of AMD processors where you have multiple NUMA nodes per socket, we will update fasterdata.es.net with the correct tuning parameters. And then again, we would use that as our standard of this is how you do that transfer. The EScp tool in turn supports all of those optimization parameters. Although currently it's missing a syntax to support multiple NUMA nodes on the same socket. So that is a feature that will be coming shortly. And yeah, there's a little bit more to tuning EScp, but I think that this is a really good start. As I mentioned before, the goal is to provide a transfer tool with performance similar to iPerf. And I think that it does indeed do this, at least so far in my use cases. Again, it is somewhat heavily in development. So you will notice if you choose to use the tool that while it does generally work, there are times where you will get error messages. One of the more common ones right now is if you start a transfer and you stop it in a way that that stop isn't read on the receiver and you then try to resume a transfer, it will get, oh my God, this port is in use because presently, instead of having a range of ports, there's just a single port that it uses. And if the port is already in use, well, it's like, oh yeah, the port's in use, I don't know what to do. In most cases that will clear up, at which point you can then resume your transfer and it would work as you would expect it to. But yeah, a little rough around the edges. As I already mentioned as well, since it was originally designed as a diagnostic tool, you can use it as a diagnostic tool. So it has all of the flags in there for picking engine, picking the block size, choosing how you want to write that data, doing NUMA optimizations, so on and so forth. You can also use it instead of as part of an EScp transfer where a bunch of stuff is happening behind the scene. You can run it from the command line. You can give it the same set of arguments that you would get through EScp and sort of look at where in your setup things are working the way they should, where they're not. And when it does this transfer, it does try to do a lot of things that you would expect out of a modern transfer tool. So right now that includes things like checksumming of each file that gets sent. Checksumming, no matter how you do it, has a non-zero overhead on that transfer performance. And in a lot of ways, because encryption is supported out of the box, you sort of don't need to do checksumming as well. But the idea of the checksums that get sent along are that for each file you transfer, you have a checksum for that file, in addition to having the per block checksums that you get through encryption. And it's just sort of an extra level of redundancy when you're using a tool that is sort of in development, that the final data matches the source data. Additionally, this is meant to be a modern approach at data transfer. So in a lot of this, I try to avoid the terminology, this is a file transfer tool. It's really meant to be a data transfer tool. So it exposes that through its block API. That means that you can do anything where if you take a block of data, you can fill that block with your own data. You can transform it into something like S3, so on and so forth. So it provides that shared memory interface. It also provides somewhat of an API. So the API is sort of a text stream. So if you open the DTN tool in managed mode, you can start talking to it either using a keyboard or an application, and you can tell it about files that you want it to transfer, how you might want it to transfer those files, so on and so forth.
So we have another question that came in.
Sure.
This is an authentication-based question. Joe was curious, for authentication purposes, is it just SSH, or do you have the ability to tie it into something like CI login?
So the EScp tool itself is right now purely SSH. There is hope at some point in the future that it won't be just SSH. And the way that you would do that, at least right now, is if you were to write against the DTN API directly, you could start a transfer on the receiver and then, start the daemon, because each of these transfers requires that you start the DTN executable on both the receiver and the sender. So you start on the receivers, initialize that, give it a crypto key ideally, and then do the same thing on the sender, and then your transfer would commence. It's just a question of how complicated that is right now. Part of this talk is I was hoping to get feedback on like features that people would like, and how they would like that to be implemented. So this is absolutely the place for like, if you're like, oh yeah, this seems kind of broken, happy to add it as a to-do and getting a fix out. So yeah, future direction. I think I just said it, but it is hoped that this application will be largely shaped by you and your needs. There are, of course, features that I, as the developer, would like. And just another caveat here that this is meant to be something that's useful. This is not a tool that is officially supported by the Department of Energy or by ESnet. It's just a side project that came out of this earlier work and became something that we chose to develop because people are like, oh yeah, this is a tool that is useful and it would be kind of awesome to be able to do this. Right now, the tool is really two things. It's this Python script that I've been calling EScp and the data transfer tool. The data transfer tool is written in C. It has some dependencies. When you build it, all those dependencies get pulled in automatically. I think right now there's 3, maybe 4 dependencies. So the encryption library, encryption here is done using the Intel storage architecture library, specifically the crypto branch of that, since there's 2 branches. The NUMA pinning that happens is another library that gets pulled in, along with the URing library for the URing engine. Probably this is a Linux only tool at the moment because there hasn't really been much effort in porting it outside of that. At some point in the future, it is expected that this will not just work with Linux, it will work with the larger Unix flavors out there, including macOS, as well as Windows. The big switch that I would like to see before we start supporting different operating systems is a move from having this be a Python-based script to more of a combined application. My initial thoughts on that were to have the Python script be replaced with a Rust executable. Rust has one of the benefits of compiling to something that's close enough to C that it is able to call C code as a standard function with the same overhead of calling a standard C function through C. So you would have a sort of high-level language to handle all of the complicated things like file IO, API accesses, that sort of stuff that typically are well out of the scope of what you would do in a C application. So handle all those high-level tools while still being fast and being able to tie in directly to the DTN script. And when I say tie in, I mean it statically linked to the DTN script and then call those C functions directly. And then in the not too distant future, I mentioned how AMD sort of changed the way we look at sockets. It used to be you would look at a single socket on a single socket as being a single entity which you code against, whereas now inside of a AMD server socket, you have a bunch of chiplets. Each of the chiplets is in effect its own historically was it like, if I were to say what a socket used to be, AMD socket is composed of multiple CPU sockets, each which are largely independent. So we do need to reflect that design in the EScp tool. That's sort of a really easy thing to do because we sort of have this architecture where you already pin threads to a memory region. You just have to be a little bit more specific. That's the revised syntax for NUMA nodes, where you will have a CPU mask, a memory node, and then the number of threads that would apply to that stanza. And as the DTN application would get initialized, it would just pick threads from that particular node until it's full and then go on to the next, and so on and so forth. And then the very last thing I have here is, if you are interested in this code, this is where you go to get it. github.com ESnet/EScp. I think there are some tools on GitHub where you can raise issues. I don't really have a like forums set up, but I am hoping that the GitHub tool itself provides enough feedback that we can hopefully build a little bit of a community around it, and start to get people using it. So do I have any questions from people?
So thank you, Charles, for going through all of that. Right now we are empty on questions, but I'll put the call out. If anybody does have anything that they want to ask, certainly put it into the chat room. I'll put in a second request there. If anybody thinks that this would be useful to test with any of your users or just yourselves personally, maybe make yourself known in the chat and we can follow up with you afterwards. So I had a couple of things that I jotted down until people get their questions typed in. So with respect to sort of the difference between AMD and Intel, is this eventually going to mean that you're going to have to start creating different binaries to support this, or is it something that would just be sort of taken care of at compile time? Yeah, I'm just curious because I don't actually know what the difference is going to be in the future when we start to have this much divergent requirements for chips and things like that.
No, it's just the tuning process is slightly different on AMD versus Intel because of obviously the underlying architecture is different. In terms of the actual binary, whether it's compiled for Sandy Bridge versus AMD versus whatever else, performance is generally going to be about the same. In general, AMD supports the same extensions with similar performance compared to the Intel processors. In terms of the actual optimizations, again, that just changes slightly. And I feel like our AMD guidance is a little, well, I don't think that we have any right now, but in the near future, if you go on faster data, we should have guidance on that revised tuning, and then the EScp tool will support that.
Okay. And Joe just typed in, while AMD and Intel rule the HPC market today, have you considered ARM in your architectural thoughts?
Yes, that's sort of a longer term. I would absolutely like to support that. From my perspective, you start running into issues with the libraries that we're using. So right now, for encryption, since we're using the Intel storage architecture library, I think that limits us to AMD processors. There's also a slightly different memory model when you move to ARM versus Intel. I don't know if we would be affected with that with our existing design, or if that's something that is totally like outside of the scope of this. But as ARM picks up in the server market, I would expect that that is something that I would like to support. We don't even have ARM hardware to test on presently, so.
Okay. And we don't have any other questions right now, so I'll put in a last call here. If anybody has anything that they'd like to say, please type it in. While we're waiting for a couple minutes here to see if anybody else types it in, I'll thank Charles again, and we'll make sure that we get the slides posted and the video posted. And I'll make sure that that link to EScp gets shared in the email that we send around, and then people can contact us if they're interested in downloading that or adopting that. All right, it looks like we may be out of questions. So thanks again for taking the time to come in and listen to this today. For those that are still on, next week's talk is going to be Hans Ottoman from IU's International Networks program, and he's going to be talking a little bit about the EPIC Roadside Assistance Program. So hope everybody has a good week and weekend, and we will talk to everybody next week. Thanks again, Charles.
Yeah, thank you everyone for joining. I hope you enjoyed the talk.